Correlation and regression is an extremely important part of the scientific process. Being able to study the relationship between two sets of variables and then from that make some conclusions or some predictions on what might happen later down the line. At GCSE, you would have been asked to comment on the strength of a correlation, whereas at A level we've got the product moment correlation coefficient, or the PMCC for short. And what this is it gives you the exact numerical value of a correlation between two sets of data. The advantage of this makes it much easier to compare different correlations between different graphs to see which one's stronger and weaker, because you simply have to look at which numbers are bigger or smaller. Now the value of R, the PMCC, lies between -1 and 1 inclusive. If it's 1, it's said to have a perfect positive correlation, which means that all the points would line a line with a positive gradient. And if it was -1, it'll be a perfect negative correlation. A value of 0 means that there's no correlation at all between the two variables. And you can see on the left hand side here some examples of scatter graphs and their respective values of R. Now the way to calculate this, usually you get a list of data that you'll put into your calculator and then it will give you the value of R, and we'll come on to that a bit later on. But another way they can give you the data is they can say SXY is equal to this and SXX is equal to this. And the way you go about this is in the formula booklet, R is equal to SXY over the square root of SXX times by SYY. And simply just plug in these values in and you will get the value of R for that particular data. So we can see an example of a question here. This question is actually unique in the sense that it gives us a list of data, so we could have typed it into the calculator if we wanted to, or to save time, it's already given these values, so we could have also substituted it into the formula. Either method would have awarded us the value of R and we would have got full marks for it. Now let's just see an example of some questions involving this. So in this one, January 2012, it says that Lenny has been asked to calculate values of product moment correlation coefficient. And it wants us to comment on whether we think these are going to be definitely correct, probably incorrect, or definitely incorrect. So if we take the first one here, 0.365 between height and waist measurements. So this means that there's a weak to moderate positive correlation between the height and waist measurements. So this means if somebody gets taller, you expect their waist measurement to increase maybe slightly. Now this is probably correct because it would make sense that if somebody was getting taller, their body would be a bit bigger, so therefore they might end up with a larger waist. But obviously it's not a perfect correlation, which is why we've got quite a low value. And the next one, it says 1.16 between height and weight. Now this is definitely incorrect because we spoke about earlier, R must lie strictly between 1 and -1. And the last one, -0.583 between weight and waist measurements. So this means that as somebody's weight increases, their waist measurement decreases, which means it's probably incorrect because you'd expect the reverse to be true. Now it isn't definitely incorrect because we don't know what sample they're dealing with when he calculated this, but that's why it's probably incorrect as opposed to definitely incorrect. And let's have a look at this final one here. So in this one, we've been given two scatter diagrams and we need to try and make predictions on what the values of R are based on just looking at these scatter diagrams. And I'll throw the values up that it allows. So anywhere between 0.6 and 0.98 would have gave you the mark for part I, and anywhere between -0.5 and -0.02 would have gave you the mark for part II. Just like earlier on with the PMCC, we were able to work out the exact value of the correlation. In this one, the least squares regression line is our line of best fit, but we're able to work out the exact equation of the best line of best fit to suit our data. Now first thing it's worth pointing out that there's two forms this could come in, either y is equal to a plus bx or y is equal to ax plus b. Now the only reason why there's two forms is statisticians usually prefer the form y is equal to a plus bx. So when they see in quoting this, a tends to be the y-intercept and b is the gradient. Whereas mathematicians, just because they're used to the idea of y is equal to mx plus c, are more used to the other equation on the other side. It doesn't make a difference which way around you think about it, as long as if they tell you to do a certain way, you write it in that particular form. And when we come to the calculators in a bit, you'll see that there are two options to use either one of those two methods. Now, other than the calculator, you can also calculate it using SXY and SXX, etc., just like with the product moment correlation. And this can be found in the formula booklet. So we can see here that B, now it's important to recognize on this time that B is referring to the gradient. b is equal to sxy over sxx. Whereas the value of a, this is equal to y bar, take away b, times by x bar, where y bar and x bar are the mean of the x and y respectively. Let's just have a quick look at a question and the way it could come up. So in this first one here, we've got a list of data and it says calculate the equation of the least squares regression line y on x. So all you're going to do is just plug all of these numbers into your calculator and it will spit out the answer of r. Whereas this other example here, instead of giving us a list of data, as we mentioned a second ago, it tells us what sxx is and sxy, x bar and y bar. So all we need to do now is just use that formula from the formula booklet, plug all these values in, and we can work out what a and b are respectively, and therefore get our least squares regression line. So let's have a look at calculating correlation and regression on our calculators. And the way we're going to do that is we're going to go to Start, and then in here we're going to write down list 1, list 2. Now just before we do, let's just double check. If you go to Calc, Set, it should say list 1, list 2, list 1, list 2, 1. Again, if it's a factory setting calculator, it may say 1 in the one variable frequency, so you need to change the list 2 for this to work. We just come back out. So what we're going to do now is you put all your x values in list 1 and all your y values in list 2. So I'll just make some up. So any sort of values here, like so. Now, if I was to hit calc regression now, it will come up with a dimension error, and the reason why is because I've got one of my rows with only one value in. So we need to make sure that there's values in all of them. Now the way we do this is we go calc, F3 for regression, it's x, which is F1, and then we get these two options. We've got ax plus b and a plus bx. And we spoke earlier on about the fact there's two possibilities. Now in stats, they usually want you to use a plus bx, but it doesn't make a difference because if I was to press the other button, I'd just get my a and b the other way around. But if I press this one here, we'll get this. Now my a, this is my y-intercept, that's going to be 9.169. My b, which is my gradient, is minus 0.711. And this particular data has got a value of r to be minus 0.533. And these are the values that I would write down. Alright then, to explain what a residual is, we must first remember that using our line of best fit, our least squares regression line, we can make predictions. So for example in this, we've made a prediction at x equal to 20, and then that would have read off a value of 104 from the y. And we're using this line of best fit to do so. Now the residual is the difference between your prediction and the actual value of the data. So if we see here, at the value x equal to 20, we actually had some data, and that had a coordinate of 2096. So that was the actual data when x was 20, whereas we got a predicted data of 104. The residual is the difference between those two. Specifically speaking, it's the actual data, in this case 96, take away the predicted data, which was 104. So this is a negative residual, which means it lies below the line of best fit, of a minus 8. So we're going to cover interpreting some of your results. Now unfortunately for this particular topic, there's a lot of variations that could come up, but hopefully we're going to cover them all here. The first which is interpreting your PMCC. So if we have a look at this question here, it says interpret your value of r in context to the question. Now whenever it says context, you need to refer to the context of the question itself. Now earlier on we would have worked out r, we would have got 0.498 here. So what we would say is we'd say it's a moderate / some positive correlation. We need to mention positive correlation and we need some mention of the strength, in this case probably a moderate. Then we bring the context in. So it's a positive correlation between, and then this is where we write it down, it's annual electricity consumption and the annual gas consumption for bungalows. Now it's worth pointing out that in the more modern day exams, the examiners are getting quite picky with what they accept here. So for example, if a student wrote down between electricity and gas consumption, you may not have got the mark. Make sure you include the full details of what it is between. We'll have a look at another one of these. So in this one you can see interpret value of r. So we got r to be minus 0.326. In this case we'll say it's a weak / some negative correlation, and it's between the percentage of marks on paper 1 and the percentage of marks on paper 2. Again, include the full details of what the variables are representing. The second one we could be asked to do is this interpret the values of our a and b for our least squares regression line. You can see this question that's saying interpret your values of gradient and the intercept, which is our A and B. And we would have got values y is equal to 1.3 plus 0.405x. So the first thing we can say is a gradient of 0.405. This means that for every change in x, our y is going to change by 0.405. So in context of the question, this indicates that for every tile, because the tiles were their x, he replaces, it takes an average of 0.405 hours, which was a y, to do so. Change in x is equal to change in y. Next part, y-intercept of 1.3, this indicates a time taken when we have no tiles to fit. Okay, so x is equal to 0. So it indicates the time taken to replace 0 tiles, so this could in context represent the startup time, or him getting prepared to do so. If we have a look at another one, in this case we've got y is equal to 5.35, take away 0.0758x. Now here we've got a negative gradient, so this means that for every change in x, our y is going to go down, it's going to decrease by 0.0758. So we can say here that for every percentage of moisture content, the calorific value decreases by 0.0758 megawatt hours per ton. The y-intercept, in this case, this is going to indicate the calorific value when there is no moisture in the wood, or when it's dry. The third type of question we could be asked to do is regards to interpolation and extrapolation. So this is where we're going to make predictions using our least squares regression line, and there's two types of predictions that we could do here. The first is interpolation. This means that we are making our prediction inside the data set that we use to calculate the least squares regression line in the first place. Now this is generally considered quite an accurate prediction because it's within the data set, so you're assuming the values should be quite accurate, assuming obviously that it does have a correlation. Whereas extrapolation, this is where you're going to make a prediction into the future, or actually into the past as well. It's something that is outside of your data set, and this is generally considered quite a poor approximation because you don't know whether the trend line will continue. And quite often in examinations you'll be asked to comment on these. Let's see an example of this here. So you can see here, give a general reason why your equation should not be used to estimate the wood's calorific value when it's got a moisture content of 80%. Now if we look at our x values there, it goes from 5 to 65. So the number 80 is outside of our data set. So this means it is an extrapolation. While we're here, we'll have a look at the second part. It's saying give a specific reason based on the context of the question and with numerical support why your equation cannot be used to estimate the wood's calorific value when it's got moisture content of 80%. The reason why is when you actually put 80 into your equation, you would have got a value of minus 0.8. Minus 0.7, and this indicates that it's got a negative calorific value, which is impossible in context of the question. The next one is residual. In this question here, it says, given that the values of the 13 residuals lie between minus 0.28 and positive 0.3, comment on the likely accuracy of your estimate in part D. Now remember, your residuals, that's the difference between your predicted data and your actual data. So the smaller they are, the better your predictions. And in this case, with minus 0.28 and positive 0.23 being the largest values they could be, we would say that this is actually quite an accurate result because the residuals are relatively small. Another example of this, given that the values of 12 residuals lie between minus 7 and 9, again if we look at the y values here, our y values range from 242 to 412. So being out by a maximum of 7 or 9 is relatively small, so we can say that our predictions are relatively accurate. Another one that could come up, although rare, is interpreting new PMCC values. So for example, one of the problems with the product moment correlation coefficient is it can be affected quite heavily by an outlier and extreme data. And sometimes in questions they may get you to calculate this. But then they may say, they may ask you to remove it or just calculate a product moment correlation with just half the data. So you can see it, if the outlier is removed, then the correlation is a lot stronger. And in this case, we get R to be 0.7. So it's just recognizing the result that sometimes if you might have one or two extreme values, and if you remove them, you actually might get quite a strong correlation between the different data sets. And this is one of the advantages of sketching a scatter diagram, because you can see results like this. And the very last part is response and explanatory variables. Now, a response variable, this is a dependent variable that is affected by changes in other variables. So something that is completely dependent on everything else. The explanatory variable, this is independent and is unaffected by other variables. If we see some examples here, okay, so think about the number of ice creams sold and the weather. So we were comparing those two. And you'd expect there to be a correlation because as the weather gets hotter, you expect to sell more ice creams. As the weather gets colder, you probably won't sell that many. But it's very important to understand which one is a response and which one is explanatory. The response variable is ice cream sold because as the weather gets hotter, the number of ice creams you sell increases. It doesn't mean that if you sell more ice creams, the weather's going to get hotter. It doesn't matter how many ice creams you sell, it's not going to affect the weather, which is why the weather is independent of this variable. So the weather is our explanatory. Another example, amount of money a footballer earns and their ability. So if you've got somebody that's pretty good at football, chances are they're going to be paid a higher wage than the other players. But that doesn't mean that if you would just give that player a massive pay increase, then their ability is going to increase as a result. Unfortunately, it doesn't work that way. Let's cover some of the important points you need to remember for correlation and regression. And the first of which is the formula. So remembering that sometimes you're going to be given SXY and SXX, Y bar, X bar, and so on, and just making sure you know how to calculate the values of R, the values of A and B respectively. Second point is interpreting A and B. Now, A and B is your gradient and your y-intercept. Remembering the change in gradient, this means that for every change in x, your y is going to increase or decrease by the gradient amount. Whereas your y-intercept, that's when x is equal to 0. And always refer this to the context of the question. Part 3 is interpreting your PMCC. So again, the two things you've got to write here is firstly you've got to talk about if it's a positive or negative correlation or possibly no correlation and its strength as well. And then it's between, and always make sure you write out in full what it is between, what's your value of x and what's your value of y, what is it lying between. The fourth one is making predictions, so taking your least squares regression line and being able to make predictions from there, and then if required, commenting on whether that is interpolation or an extrapolation, and also saying whether that's a good or bad thing. Interpolation is obviously relatively accurate, whereas extrapolation isn't. Part 5 is the difference between a statistical reason and a reason in context. So quite often you'll be asked to do both of these. A statistical reason, this might be, for example, talking about interpolation or extrapolation, might be referring to the strength of your product moment correlation coefficient and so on. Whereas a reason in context wants you to ignore all the numbers and simply just look at the context of the question and try and think about what it is that isn't working or is working here. Part 6 is revising your values of your PMCC. So it's the idea that sometimes you might have an outlier that is affecting it quite a lot or more than one outlier. And once you remove it, you might get a much stronger correlation coefficient. Just being able to understand what this means. Part 7, change of scale does not affect your PMCC. So for example, if you worked out a product moment correlation coefficient between the heights and weights of individuals, it doesn't matter whether you worked out with metric units or imperial units, or you upscaled it to something else, you will always end up with exactly the same PMCC. Part 8, given that residuals are between. So this is a comment section, the idea that it's going to say we've got the residuals lie between here and here. What does that mean on the accuracy with it? So you need to look at your residuals and look at the size of them relative to your y values. If they're relatively small, then it's going to be quite a positive, quite an accurate prediction. Whereas if they're quite large relative to your y values, then it means that your prediction probably isn't very accurate. Question 9, the sum of all the residuals. Now this doesn't come up that often, but it's worth noting that the sum of all the residuals is always 0 for anything. Part 10, state an advantage of plotting a graph before calculating the PMCC. Now the advantage of doing so means you can see outliers. You can see this extreme data, you can see if it's been affected by something. Other things, for example, is you could be identifying non-linear patterns. So there is at times when you will end up with, although it won't happen in S1, you will get some sort of correlations where it's not a line, instead it might be a curve and things. And other examples, for example, you could estimate the value of R. So when you actually work out your value of R, you can see whether it's correct. And the last part, response and explanatory variables and understanding the difference between the two.